This is my review of roughly the second half of Unit 2, Forces and Translational Dynamics for AP Physics 1. This is about universal gravitation, the spring force, and circular motion.
Flippin' Physics!
This video is a free portion of my AP Physics 1 Ultimate Review packet. If you are planning to take the AP Physics 1 exam, I definitely recommend you get my full AP Physics 1 Ultimate Review packet. Link is in the video description. Now, Bo, what is the equation on the equation sheet for Newton's law of universal gravitation?
The equation is the magnitude of the gravitational force equals the gravitational constant.
Big G!
Or big G, times the mass of object 1, times the mass of object 2, all divided by r squared. And realize, class, r is not
The radius!
R is
The distance between centers of mass of the two objects.
This can be confusing because sometimes r is
The radius!
Well done.
And big G, the gravitational constant, equals 6.67 times 10 to the negative 11 newtons times meter squared over kilogram squared.
But we do not have to have that memorized because it's on the table of information we'll get when we take the exam.
I know, but I do have it memorized.
Right.
I thought I had it memorized.
Thanks, everybody. The two m variables in the equation represent the gravitational masses of the two objects which are interacting via the gravitational force. And we already talked about r. Realize the gravitational force is always directed along a line connecting the centers of mass of the two objects, with the gravitational force on each of the two masses always being directed toward the other mass. And, just to be absolutely clear, the gravitational forces acting on both masses have the same magnitude and are a Newton's third law pair. Alright, now let's talk about the narrow band of altitudes in which humans live on this planet. In that location, where you most likely are right now, the local gravitational field, little g, is nearly constant, and we can treat the local gravitational field as constant with negligible error. And realize the local gravitational field is directed downward toward the center of the planet. One way to determine the gravitational field is to use the equation for the force of gravity acting on an object in a constant gravitational field. The force of gravity equals gravitational mass times the gravitational field strength. That can be rearranged to show that the gravitational field strength equals the gravitational force divided by the gravitational mass.
I thought he said last time that we were not really going to distinguish between gravitational mass and inertial mass in this class.
He's probably just being thorough.
Yeah, that sounds like Mr. P.
Yep. I do want to look more carefully at that force of gravity equation. Gravitational force equals mass times gravitational field strength.
Not that time, though.
Nope.
There is a subscript missing from the mass in that equation. What do you think that subscript is?
G for gravitational mass?
No, I do not think that's what is missing.
Object. That is the mass of the object the gravitational force is acting on.
Sure, that makes sense.
Right. But I thought all forces were interactions between two objects. If that mass is the mass of the object, what is the other mass interacting with the object to cause the gravitational force?
The planet creating the gravitational field.
Yeah.
Yeah.
That makes sense. And a more general way to derive the equation for the gravitational field, little g, which surrounds the surface of a planet, is to use the gravitational field equation and Newton's law of universal gravitation. Both are the force of gravity acting on an object, so we can set the two equations equal to one another, with the two masses in Newton's law of universal gravitation being the mass of the object and the mass of the planet.
Everybody brought the mass of the object to the party.
Everybody brought mass.
And we get that the gravitational field which surrounds a planet equals the gravitational constant,
Big G!
times the mass of the planet, all divided by the square of r, the distance between the centers of mass of the two objects. However, considering the location we are talking about is on the surface of the planet, the distance between the center of mass of the planet and the center of mass of the object is, with negligible error, equal to the radius of the planet. And if we move far enough away from the surface of the planet, we need to add the altitude of the object to the radius of the planet within the parentheses in the denominator. Okay, Billy, talk about what happens if the only force acting on an object near the surface of a planet is the gravitational force.
Absolutely. An object is near the surface of a planet, so it is in the constant gravitational field of magnitude little g, and the only force acting on it is the force of gravity. Okay, we know the only force in the free body diagram of all the forces acting on the object is the force of gravity pointing straight down. That means the net force in the y direction equals the negative of the force of gravity, negative because the force of gravity is down. And it also equals mass times the acceleration of the object in the y direction because it's Newton's second law. We can substitute mass times gravitational field strength in for the force of gravity, and everybody brought the mass of the object to the party.
Everybody brought mass.
And we get that the acceleration of the object in the y direction equals the negative of the gravitational field strength. Oh, this is an object in free fall. The object has an acceleration in the y direction equal to negative little g, the gravitational field strength. And we also call little g the acceleration due to gravity. Because any object in free fall has an acceleration with a magnitude equal to little g, which is caused by the force of gravity of the planet acting on it. And that's why little g is also called the acceleration due to gravity. That's so cool!
Yep. And remember, on the AP Physics exams, we can approximate little g to be 10 meters per second squared. It just makes all the calculations easier.
I thought the units for gravitational field strength were newtons per kilogram.
They are the same. Newtons are kilogram meters per second squared. Substitute that in for newtons. Kilograms cancel out. And you show that newtons per kilogram are the same as meters per second squared.
Oh, yeah.
Hey, you.
Me?
No, you.
Me?
No, you.
Oh.
You should subscribe to Flipping Physics and like this video.
Yeah.
It is helpful for Mr. P.
Yep.
Thanks, y'all. It is. Next up is the spring force. The basic concept is that an ideal spring force is proportional to its displacement from equilibrium position. In equation form, that is known as Hooke's law and is the spring force equals the negative of k times delta x. K is the spring constant and is a measure of how much force it takes to compress or expand a spring per meter. In other words, a larger spring constant will have more resistance to changes in distance from equilibrium position. Typical units for the spring constant are newtons per meter, and the spring constant is always positive. And delta x is the displacement of the system or object from equilibrium position or rest position. The direction of the spring force is always toward equilibrium or rest position. Also, the negative in Hooke's law means that the force exerted by the spring and the displacement of the object from rest position are opposite in direction. It is important to realize that an ideal spring, which is, unless otherwise stated, what we work with in AP Physics 1, has negligible mass. And lastly, the magnitude of the slope of a graph of spring force versus displacement from equilibrium position is the spring constant.
Wait a second. Mr. P just said that the spring constant is never negative, and yet he also just said that the slope of a graph of spring force versus displacement from equilibrium position is the spring constant.
Actually, that's not quite what he said. If we graph data for a spring, we can see what he said. That the magnitude of the slope of the trend line for the data of spring force versus displacement from rest position is the spring constant.
Right. I see it now. Thanks.
You're welcome.
Nice. And the last major topic of this review is circular motion. There is a small section in Unit 2 about the basics of circular motion, but do not worry. There is a heck of a lot more about circular motion and things moving in circles and rotating in Units 5 and 6. All right, circular motion. The linear velocity of an object moving along a circular path is called tangential velocity. And the tangential velocity of an object is always directed perpendicularly to the radius describing the path. And the tangential velocity is always parallel to the path itself. An object which is moving along a circular path must have a centripetal acceleration which is always directed inward toward the center of the circle. Average acceleration equals change in velocity over change in time, and velocity is a vector, which means it has class both
Magnitude and direction.
Therefore, the reason an object moving along a circular path must have a centripetal acceleration is because the direction of the tangential velocity of the object is always changing. Therefore, the tangential velocity is changing. It is not constant. Therefore, there must be an acceleration of the object, and that acceleration is, again, centripetal acceleration. The equation for centripetal acceleration is centripetal acceleration equals the square of the tangential velocity divided by the radius of the path the object is moving along.
Mr. P,
Yes, Bobby?
why is the t subscript not on the tangential velocity in the equation for centripetal acceleration on the equation sheet from the College Board?
I do not know.
Okay.
Yeah. Moving on. An object moving along a circular path at a constant speed can be defined using the terms period and frequency. Bobby, please tell me about period and frequency.
Okay, period is defined as the time it takes for an object to complete one circle, and the symbol for period is capital T. Frequency is defined as the number of revolutions completed by an object per second, and the symbol for frequency is lowercase f. The units for frequency we typically use are cycles per second, which are called hertz, which are abbreviated as capital H lowercase c. Those two terms are inversely related to one another. In other words, period equals 1 over frequency.
Well done, Bobby. Thanks. Bo, please start with the equation for speed and derive the equation which relates the period of an object traveling at a constant tangential speed in a circular path in terms of radius and tangential speed.
Okay. Average speed equals distance over time. We're talking about an object moving at a constant tangential speed, so tangential speed equals, considering period is defined as the time it takes for an object to complete one circle, let's put period in the denominator and the linear distance an object goes through when it goes through one circle in the numerator, which is the circumference of the circle. The equation for circumference is 2 pi times radius. Therefore, the period of an object moving in a circle at a constant tangential speed equals 2 pi times the radius of the circle path the object is moving through, divided by the tangential speed of the object.
Are you really going to use v sub t for tangential speed?
Yep.
Yeah, it is not great, however, that is usually how it is written. Centripetal force is the net force in the indirection or the center-seeking force which causes the centripetal acceleration of the object in towards the center of the circle. The equation for centripetal force is net force in the indirection equals mass times the acceleration in the indirection, which is the centripetal acceleration. Class, what are 3 things I asked you to remember about centripetal force?
The centripetal force is not a new force. It is simply the net force in the indirection.
The centripetal force is never in a free body diagram because it is not a new force. It is just the net force in the indirection.
In is positive. Fine, I'll elaborate. When summing the forces in the indirection, forces which act inward are positive, and forces which act outward are negative. Better?
Yep.
Yes.
Perfect. Thank you very much for learning with me today. I enjoy learning with you.
I know, but I do have it memorized.
Right.
I thought I had it memorized.
Beautiful.
All right.
Well done, everybody.